Tonight, we're going to explore one of the boldest ideas in all of physics, a real way to travel faster than light. The nearest star is so far away that light itself takes more than 4 years to reach it, and our fastest spacecraft would need tens of thousands of years to get there. For all of human history, the stars have been out of reach, until now. In 1994, a young physicist named Miguel Alcubierre was watching Star Trek when it hit him. What if a starship never moves through space at all? What if it bends space around itself instead, shrinking it in front and stretching it behind, and rides the warp like a surfer on a wave? He turned that idea into a real solution to Einstein's equations, and it worked. A bubble of space-time that could outrun light, with nothing inside it ever breaking the cosmic speed limit. For 30 years, it stayed locked away in theory. Then, in 2024, a team at Applied Physics changed the conversation. For the first time, they showed that a warp drive built from ordinary matter may be possible without breaking a single law of physics. By the end of tonight, you're going to understand how Alcubierre cracked the door open, what the 2024 breakthrough actually proved, and just how close we may be to building the first true starship. Not science fiction, not impossible, just very, very far away. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Very far away. That phrase does a lot of work in astronomy, but most of the time, it doesn't land. We hear it, we accept it, and we move on without ever feeling what it means. So let's make it real. The nearest star beyond our sun is called Proxima Centauri. It sits in the constellation Centaurus, visible from the southern hemisphere. It is a small, dim red dwarf, much fainter than our sun, and by cosmic standards, it is our closest neighbor. The distance between us and that neighbor is 25 trillion miles. That is 25 followed by 12 zeros. If you tried to write it out, the number would stretch across a page. To understand what that distance means, start with light. Light travels at 186,000 miles per second. That is not a speed we experience. It is the universe's absolute speed limit, built into the fabric of reality itself. At that speed, a beam of light could circle Earth's equator more than 7 times in a single second. A photon could travel from New York to Tokyo and back in less time than it takes to snap your fingers. Light is the fastest thing that exists, and nothing in the universe can move faster. Now, send that beam of light toward Proxima Centauri. The journey takes 4 years and 3 months. A light beam that left Proxima Centauri right now, moving at 186,000 miles per second, without pause, without deviation, would not reach Earth until the year 2030. That is how far away our nearest neighbor is. Even at the speed of light, it is a multi-year trip. But we cannot move at the speed of light, not even close. So what can we do? Here's what scientists and engineers have actually achieved. On September 5th, 1977, a spacecraft called Voyager 1 lifted off from Cape Canaveral, Florida. It was designed to study the outer planets. It visited Jupiter. It visited Saturn. Then it kept going. It has been going ever since. And on a specific date in August 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind, the stream of charged particles flowing outward from the sun, gives way to the interstellar medium, the thin gas and dust that fills the space between stars. Voyager 1 became the first human-made object ever to enter interstellar space. That is not a small thing. In the entire history of our species, nothing built by human hands had ever reached that boundary before. Voyager 1 currently travels at about 38,000 miles per hour relative to the Sun. That number is worth sitting with for a moment. A commercial airliner flies at roughly 600 miles per hour. The thrust SSC, the land speed record holder, reached about 760 miles per hour. A high-powered rifle bullet travels around 2,000 miles per hour. Voyager 1 moves at nearly 19 times the speed of that bullet. It covers approximately 333 million miles every year. At that speed, it could carry you from Earth to the Moon in under 7 hours. It could reach Mars in a matter of weeks when Mars is near its closest approach. 38,000 miles per hour. 333 million miles per year. These numbers sound extraordinary. They are extraordinary by every standard that matters in our daily lives. But here's where it gets strange. Run the arithmetic against Proxima Centauri's 25 trillion miles. Take that number, divide it by 333 million miles per year, and follow where it leads. The answer is roughly 70,000 years. Not 70 years, not 700 years, 70,000 years. Civilizations have risen and collapsed inside that window. Modern humans did not begin painting cave walls until about 45,000 years ago. Agriculture is only 12,000 years old. Everything we call history fits inside a fraction of the time it would take Voyager 1 to reach our nearest stellar neighbor. Not fast enough. Not even close to fast enough. And Proxima Centauri is the nearest one. Sirius, the brightest star in our night sky, sits 8.6 light-years away. At Voyager speed, reaching Sirius would take around 150,000 years. Betelgeuse, the red star marking the shoulder of Orion, lies roughly 550 light-years from Earth. Our sun will eventually exhaust its hydrogen fuel, swell into a red giant, and consume the Earth in that process, all before a Voyager-class spacecraft traveling at 38,000 miles per hour could reach Betelgeuse. The speed that felt extraordinary a moment ago turns out to be essentially meaningless. That is the real wall. Not a wall of engineering, not a wall of fuel, not a wall of political will. A wall of physics and arithmetic. The distances are so vast that even our fastest achievement, the object we launched with the most velocity we have ever given to anything, moves so slowly by comparison that it might as well be standing still. This is the problem that every concept in this conversation is trying to answer. And the answers, as you are going to find, are stranger and more demanding than almost anyone imagined. So the question becomes obvious. If the distances are that enormous, why not simply build a better engine? Why not pour more fuel into a larger rocket, push harder, go faster? It seems like the kind of problem engineering should be able to solve. It is not. The obstacle is not the size of our engines, it is not the quality of our fuel, it is physics itself, and physics does not negotiate. Every rocket ever built works on the same principle. You carry fuel, you burn it, the exhaust shoots backward, and the spacecraft moves forward. That is the whole idea. But here is the problem buried inside that idea. Fuel has mass, and mass has to be accelerated just like everything else. So to push your fuel, you need more fuel, and to push that fuel, you need even more fuel. The relationship is not linear, it is exponential. Engineers call this the tyranny of the rocket equation, and tyranny is not an exaggeration. The more distance you need to cover, the more fuel you need. The more fuel you carry, the heavier you are. The heavier you are, the more fuel you need to carry that weight. The spiral never closes. It only grows. Think about what it took to send 3 astronauts to the moon. The Saturn V rocket, the largest and most powerful launch vehicle ever successfully flown, burned through its first stage in roughly 2.5 minutes. In those 2.5 minutes, it consumed 3 million kilograms of kerosene and liquid oxygen, 3,000 tons of fuel, gone in the time it takes to boil a kettle, just to push 3 people 250,000 miles to a neighboring world. Now consider what that comparison means. Proxima Centauri is not a little farther than the moon. It is 100 million times farther. If you tried to reach Proxima Centauri using chemical rockets in a human lifetime, the fuel requirement does not scale up by a factor of 100 million. Because of the exponential trap in the rocket equation, the numbers become something else entirely. More fuel than exists on Earth. More hydrocarbons than every oil deposit, every natural gas reserve, every organic molecule on this planet combined. You could harvest the atmospheres of Jupiter and Saturn. You could strip every asteroid and every comet in the solar system. It would not be enough. Not close to enough. So engineers and physicists looked elsewhere. And what they found, each time, was a version of the same result. Nuclear pulse propulsion was one of the more serious proposals. The idea came out of the late 1950s and 1960s, under the name Project Orion. The concept was exactly what it sounds like. Detonate a nuclear bomb behind a massive spacecraft. Let the blast push against a thick steel plate at the rear of the ship, cushioned by a system of shock absorbers. Detonate another, and another. Thousands of them in sequence. In principle, this could push a spacecraft to a few percent of the speed of light. That sounds extraordinary until you do the math. At 3% of light speed, the journey to Proxima Centauri would still take 140 years, a century and a half. And that assumes the engineering works, which it never did. Project Orion was never built. The political and environmental problems alone were enough to shelve it. But even setting those aside, even imagining it worked perfectly, 140 years is not a human lifetime. It is not a mission. It is a multi-generational commitment to a destination none of the original crew would survive to reach. Fusion propulsion offered a cleaner version of the same promise. Burn hydrogen the way stars do, fusing light elements into heavier ones, releasing enormous amounts of energy in the process. More efficient than chemical combustion, cleaner than nuclear fission. But the reality was different. We cannot do this. Not in a spacecraft, not in a power plant, not yet. Controlled fusion has been the technology of the near future for 70 years. It remains stubbornly out of reach. A fusion rocket is at minimum decades away from being a serious engineering project. And that is the optimistic reading. Antimatter propulsion sits at the far end of the efficiency scale, at least theoretically. When matter meets antimatter, the result is total annihilation. Every gram of mass converts completely to energy according to Einstein's equation, a conversion rate that no chemical or nuclear reaction can approach. In principle, an antimatter drive could push a spacecraft to a significant fraction of light speed. The problem is containment. Antimatter cannot touch the walls of any container, any surface, any material. Contact means annihilation. And beyond the storage problem, there is a production problem. The entire human civilization produces antimatter in quantities measured in billionths of a gram per year. Think about that. A billionth of a gram, less than the weight of a single cell. That is the global annual yield. You could not fuel a candle with what we produce, let alone a starship. Solar sails offered something different. No fuel at all. Instead, a vast reflective surface catches the momentum of photons, the particles of light themselves, the same way a sailboat catches wind. Light has no mass, but it does carry momentum, and a large enough sail can ride that pressure across vast distances without consuming any fuel. The Breakthrough Starshot initiative, backed by investor Yuri Milner and supported by Stephen Hawking before his death, proposed exactly this. Ground-based laser arrays aimed at gram-scale probes, tiny chips essentially, accelerating them to 20% of the speed of light. At that velocity, Proxima Centauri is reachable in roughly 20 years. The data would be sent back by laser. It is perhaps the most credible proposal on the table for sending anything to another star in a human time frame. But notice what that proposal actually describes. Not people, not a crew, a chip, a few grams of instrumentation. A crude version of the same concept would require a sail hundreds of miles across, and laser arrays drawing an enormous fraction of all the power generated on Earth. We are talking about a scale of infrastructure that has no precedent in human history, all to move a single crewed vessel to a neighboring star. Each of these ideas carries real science. Each one is a genuine attempt, and each one gets closer to the ceiling than the one before, but none of them break through it, because the ceiling is not made of engineering problems. It is made of something deeper. In 1905, Albert Einstein published what became known as special relativity. The theory did many things, but one of its central conclusions was this: nothing with mass can be accelerated to the speed of light. Not because we lack powerful enough engines, because of what happens to mass itself as it approaches that speed. As an object moves faster, its effective mass increases. At 99% of the speed of light, the apparent mass of an object has grown by a factor of 7. At 99.9%, by a factor of 22. Each small increment closer to light speed demands more energy than the last. Not proportionally more, but vastly more, like climbing a slope that grows steeper with every step, until the slope becomes a vertical wall. Reaching light speed itself would require infinite energy. Infinite energy does not exist. The wall is not a wall we can break. It is a wall that grows as you approach it. And the limit is not simply about engines or energy. Light speed is the rate at which causality itself propagates through the universe. It is the maximum speed at which any information, any signal, any influence of any kind, can travel from one point to another. It is woven into the structure of space-time at a level that makes it doubly absolute, not a speed record waiting to be beaten, a feature of how the universe works. So every door closes. Chemical rockets demand fuel quantities the solar system cannot supply. Nuclear pulse drives still need a century and a half. Fusion remains out of reach. Antimatter cannot be made or stored in usable quantities. Laser-pushed sails can move chips but not people. And behind all of them, behind every proposal, sits the same hard boundary: the speed of light. A limit enforced not by a lack of imagination or a lack of ambition, but by the laws of physics themselves. Or so everyone thought, until a young physicist in Wales asked a completely different kind of question. His name was Miguel Alcubierre. He was 28 years old. He was working at the University of Wales in Cardiff, trained originally at the National Autonomous University of Mexico, and he had a habit that most theoretical physicists would consider professionally embarrassing. He watched Star Trek. Star Trek first aired in the 1960s. Its writers gave the crew of the Enterprise a warp drive, a propulsion system that carried the ship across interstellar distances in days and weeks. They never explained how it worked. They never tried. It was a narrative convenience, a way to move the story forward. Physicists dismissed it the way physicists dismiss most science fiction. Einstein's equations forbid faster than light travel. Everyone knew this. The conversation was over before it began. Alcubierre did not treat it as a settled question. He treated it as a homework problem. He went to Einstein's field equations, the mathematical foundation of general relativity, the framework that describes gravity not as a force, but as the curvature of space and time. And he asked those equations a specific question, not whether anything could travel faster than light, something more careful than that. He asked what shape space-time would need to have for a region inside it to move faster than light, while nothing inside that region exceeded the speed of light at all. That distinction matters. It is the whole point. Einstein's speed limit applies to objects moving through space. It says nothing about space itself. This is not speculation. We already watch it happen. The universe is expanding. Galaxies are receding from us in every direction, and the farther they are, the faster they recede. At a distance of roughly 14 billion light years, galaxies recede from us faster than the speed of light. Not because they are moving through space at superluminal speeds, because the space between us and them is stretching. The distance itself is growing. This is called metric expansion, and it is observationally confirmed. Think about ants on a rubber sheet. Place 2 ants on the sheet and pull the sheet from both sides. The ants separate. They are not walking. They are not moving relative to the sheet beneath their feet. But the distance between them grows without limit, and no speed limit applies to the stretching of the sheet itself. Space can do the same thing. We have watched it doing the same thing for as long as we have been able to measure the universe's expansion. Alcubierre saw the loophole. If space can carry galaxies apart faster than light, could it carry a spacecraft? Compress space in front of a ship, expand it behind, build a wave in the geometry of space-time, and let the ship ride it. The ship does not accelerate. The ship does not move through space at all. The ship sits still inside a pocket of flat space-time while the pocket itself translates through the universe. But here's where it gets strange. To understand what Alcubierre actually built, you need to understand what a metric is. In general relativity, a metric is a mathematical recipe. It tells you the distances and intervals between points in space-time, how length and time behave everywhere in a region. Different metrics describe different geometries. The Minkowski metric describes flat, empty space, the baseline geometry of a universe with no gravity. The Schwarzschild metric describes space-time around a massive object like a star, the geometry responsible for planetary orbits and gravitational time dilation. The Kerr metric describes space-time around a rotating black hole, a more complex geometry where space itself gets dragged around by their rotation. Each of these is a solution to Einstein's field equations. Each is a valid description of a real geometry. Alcubierre built a new one. His metric described a bubble. Inside the bubble, space-time is perfectly flat, completely normal. The speed of light is standard. Time passes at a normal rate. An astronaut inside feels nothing unusual, No gravitational pull, no force, no acceleration, no sense of motion. Outside the bubble, space-time is also flat, matching the rest of the universe. The two regions look identical on their own. The action happens at the boundary between them. At the leading edge of the bubble, space contracts sharply. At the trailing edge, space expands sharply. The bubble moves because the geometry outside it reshapes. The region in front of the ship draws closer. The region behind the ship recedes. The ship itself never crosses the space between its starting point and its destination. The space rearranges instead. There is no kinetic energy in the ordinary sense. No relativistic mass increase. No time dilation. No acceleration forces flattening the astronaut against the back wall. The ship simply sits in the bubble. The bubble moves. The ship arrives. In May 1994, Alcubierre published this result in the journal Classical and Quantum Gravity. The paper was 8 pages long. Its title was The Warp Drive, Hyperfast Travel Within General Relativity. It contained tensor mathematics, not science fiction, and it demonstrated something that most physicists had not thought to look for. The statement, Einstein's equations forbid faster than light travel, was not wrong exactly. It was incomplete. Einstein's equations forbid objects from moving through space faster than light. They say nothing about spacetime itself changing shape faster than light. Nothing. The prohibition that everyone had treated as absolute applied only to one half of the problem. Not a speed limit on space, a speed limit on things inside space. Those are not the same rule. The paper became one of the most cited theoretical physics papers of the decade. It did not describe an engineering plan. It did not propose a mission. It was a mathematical proof of concept, a demonstration that a consistent, physically valid geometry of this kind could be written down, that it satisfied Einstein's equations, that it did not contradict known physics in the way everyone had assumed it would. Alcubierre had found a door where the wall was supposed to be. What lay behind that door was not simple. What lay behind that door had a price. The physics community read Alcubierre's paper carefully. Most of them read it more than once, and the reaction split almost immediately into two halves that had very little to do with each other. The first half was excitement, real excitement, the kind that moves quietly through a field and makes researchers pull out notebooks. Because the math was correct, not approximately correct, not correct in some limiting case or special regime. Alcubierre's metric was a valid solution to Einstein's field equations. Full stop. Inside the bubble, light moved at the speed of light. Outside the bubble, light moved at the speed of light. Einstein's speed limit held everywhere, at every local point in space. No violation, no contradiction. And yet the bubble as a whole could cross the distance between stars faster than any light beam following the ordinary path through undistorted space. The loophole was real. The geometry worked. A physicist could write it down, check every term, verify every tensor component, and find nothing wrong. That is not a small thing in theoretical physics. The second half was skepticism, and the skepticism came from one question. What does the bubble actually require? In general relativity, you can write down a geometry and then ask what distribution of matter and energy would be needed to produce it. The math runs in both directions. You can start with matter and calculate the resulting curvature, which is the ordinary way, or you can start with the curvature you want and solve backward for the matter. Alcubierre started with the curvature. The bubble geometry was his starting point. And when physicists solved backward, asking what kind of matter would have to fill that shell at the bubble's boundary to hold the geometry in place, the answer was immediate and deeply uncomfortable. Negative energy density. Ordinary matter has positive energy. A rock has positive energy. A gas cloud has positive energy. Even the quantum vacuum, the apparent emptiness of space, has a slight positive energy density arising from quantum fluctuations. Positive energy curves space-time inward. That inward curvature is what we call gravity. Things fall toward each other because positive energy bends the geometry of space-time in that direction. Negative energy would do the opposite. It would curve space-time outward, away from itself. Not attraction, repulsion. A kind of anti-gravity, built into the geometry of space rather than applied as a force. No object in everyday experience behaves this way. Nothing falls upward. No material in any laboratory has ever been shown to gravitationally repel. Negative energy density is not merely exotic in the way that antimatter is exotic, a substance that exists and can be produced in tiny amounts. It is exotic in a deeper sense. It has never been observed as a large-scale classical phenomenon. Its existence in the form required by the warp metric was, and remains, an open question. But the answer was stranger than expected. The bubble did not just require a little negative energy. It did not require a manageable amount that engineers might one day figure out how to manufacture. The calculations for the original Alcubierre metric returned a number so large that researchers initially assumed they had made an error. They had not made an error. The exotic matter required to hold the warp bubble together was equivalent, in mass energy terms, to the entire observable universe. Every star, every galaxy, every planet, every dust grain, every photon of light out to the farthest reaches of the cosmic horizon. All of it converted into negative energy and concentrated into a thin shell around one spacecraft. The number was not wrong. The metric was simply extraordinarily energy inefficient. The transition region at the bubble's boundary, the narrow zone where spacetime shifts from compressed ahead to expanded behind, was sharply curved. And in general relativity, sharp curvature is expensive. The sharper the gradient, the more exotic matter is needed to sustain it. The original design demanded a gradient so sharp that the cost was universe-scale absurd. Not slightly too large, not off by a factor of 10. The mass of the entire observable universe concentrated into a shell around one ship. For roughly a decade after 1994, the physics community held the result at arm's length. The paper was cited, discussed, and admired as a piece of mathematics. But the engineering connection was essentially zero, a proof that faster-than-light geometry was not forbidden by Einstein's equations is a striking and significant result. A proof that requires exotic matter on a universe scale to implement is, in practice, a proof of impossibility. The warp drive sat in a peculiar category, not ruled out, not achievable, discussed mainly in theoretical terms as a boundary case for what general relativity could in principle describe. That changed in 1999. Chris van den Broek, working at the Free University of Brussels, published a paper in the same journal that had run Alcubierre's original work. His question was simple. Did the exterior size of the warp bubble and the interior size have to match? In ordinary flat space, the answer is obvious. A 1 meter box contains 1 meter of interior. The two are identical by definition, but in curved space-time, the relationship between exterior volume and interior volume can break. General relativity allows geometries where a small exterior contains a large interior. A wormhole could in principle have a mouth the size of a doorway opening into a tunnel that stretches for thousands of light years. The exterior and interior are geometrically decoupled. One does not have to match the other. Think about the fantasy bags that appear in certain stories. The one's bigger on the inside than the outside. In general relativity, that is not magic. It is geometry. It is what curved space-time permits when the metric is constructed correctly. Van den Broek applied this insight directly to the warp bubble. He shrank the bubble's exterior to approximately 10 to the negative 15th meters. 1 femtometer. Roughly the size of a proton, the nucleus of a hydrogen atom. From the outside, the bubble would be smaller than any atom, invisible to every conventional instrument, undetectable by any ordinary means. But inside, thanks to the curved geometry stitching exterior to interior, there would be a normal-sized region of flat space. Room for a spacecraft. Room for a crew. The outside microscopic. The inside ordinary. The result was immediate. The exotic matter requirement dropped by more than 20 orders of magnitude. 20 orders of magnitude is a factor of 100 billion billion. The universe scale requirement collapsed. Not to zero. Not to something achievable. But to roughly the mass of Jupiter, approximately 2 times 10 to the 27th kilograms. 2 trillion kilograms. The largest planet in our solar system. In the language one physicist used at the time, the requirement went from absolutely impossible to merely ridiculously impossible. That is still impossible, but the distance between the two is enormous. It proved the original number was not a fixed property of warp geometry. It was a property of the original design. Change the design and the number moves. Van den Broek's version also satisfied a mathematical criterion called the weak energy condition, one of several formal constraints physicists use to identify the most pathological forms of negative energy. Alcubierre's original metric had violated it. The new design did not. This suggested that Van den Broek's geometry was, in some technical sense, more physically reasonable. There was a trade-off. Making the exterior femtometer scale required general relativity to behave classically at atomic length scales, a regime where quantum effects dominate and where no one has ever tested whether spacetime still follows the smooth geometry of Einstein's equations. That question remains open, but the movement mattered. Other researchers noticed it. José Notario proposed an alternative design shortly afterward, a bubble with no contraction or expansion at all, just a tangential flow of space-time around the ship, the way water curves around a rock sitting in a river. No compression, no expansion. A different geometry, different problems, different properties. By the early 2000s, warp drive theory had become a small but genuine research area. Papers appeared every year or two. Each one refined the geometry, tightened constraints, shaved energy budgets. The numbers stayed impossible, but the trajectory was downward. And the direction of a trajectory in theoretical physics carries its own meaning. The biggest reductions were still ahead. That downward trajectory did not slow, it accelerated. The biggest reduction in the entire history of warp drive theory came not from a university, not from a paper trading modest refinements, but from inside NASA itself. That detail is worth sitting with for a moment. While the field was making incremental progress on paper, a NASA physicist at the Johnson Space Center in Houston had been studying Alcubierre's math for years, quietly, and had reached a conclusion that none of the previous researchers had fully pursued. The geometry was not locked. The energy cost was not a fixed property of warp theory. It was a property of the specific design Alcubierre had chosen. And if the design could change, the number could move. His name was Harold White. He worked in a division called EagleWorks, NASA's Advanced Propulsion Physics Laboratory. The name sounds mundane. The work was anything but. EagleWorks was the place inside NASA reserved for the speculative edge of propulsion science. Warp drives, wormholes, exotic propulsion concepts that mainstream aerospace engineering had no interest in, but that NASA believed deserved serious, rigorous examination. If you were a physicist who wanted to spend your professional hours on problems that began with general relativity and ended with the question of whether any of it could ever be made to work, EagleWorks was where you went. White had identified something the earlier researchers had left behind. The energy requirement of Alcubierre's bubble depended on a specific feature: how steeply the spacetime metric changed across the bubble's boundary. In Alcubierre's original design, and in most of the variants that followed, that transition zone was very thin. The curvature changed sharply. Compressed space on one side, expanded space on the other, with the entire gradient packed into a narrow shell. That steep change was expensive. Enormously expensive. The math penalized it, but something else was happening. White realized the gradient did not have to be steep. The same geometric effect, compressing space ahead and expanding it behind, could be distributed across a thick boundary, a gradual transition that did the same work spread over a much larger volume. Think of the difference between a steep cliff and a long slope. The height change is identical. The grade is not. The steep cliff concentrates all the change into a short distance. The long slope spreads it. In curved space-time geometry, spreading that change dramatically reduced the integrated energy cost. That was the first modification. The second was the shape. Alcubierre's bubble was roughly spherical. White proposed a different cross-section, a torus, a donut shape, with the spacecraft riding not inside a sphere, but through the central hole of a ring. The torus geometry concentrated the warping in specific regions of the structure, and left others comparatively flat. When you integrated the total curvature across the entire bubble, the torus came out cheaper than the sphere. Not marginally cheaper, substantially cheaper. The two changes together, a thick boundary and a toroidal shape, were not independent refinements. They compounded. In September 2011, White presented these results at the 100-Year Starship Symposium in Orlando, Florida. The audience was not a casual crowd. University physicists, NASA engineers, people from private space companies, science journalists. White stood in front of that room and did not argue that warp drive might someday be theoretically valid. He took its validity as given and offered an engineering optimization. The number he announced stopped people. The exotic matter requirement, starting from universe scale, dropping to Jupiter mass after Vanden broke, now fell again. It fell to approximately 700 kilograms, roughly 1,300 pounds, the mass of a large motorcycle. In concentrated form, 700 kilograms of exotic matter would fit inside a medium-sized room. Not planet scale, not moon scale, not continent scale, motorcycle scale. The trajectory had moved from the mass of the entire observable universe down to something you could theoretically weigh on industrial equipment. The gap between that number and impossible had not closed. No one had ever produced a single gram of exotic matter. Not a milligram. Not a microgram. The distance between 0 grams and 700 kilograms, when your starting stock is 0 grams, is still an absolute wall. But impossible on a motorcycle scale is a different kind of impossible than impossible on a planetary scale. The intellectual texture of the problem had changed, and White was not finished. He proposed that EagleWorks could do something no warp drive researcher had ever seriously attempted. Not refine the theory further on paper, but test it, physically, in a laboratory. The instrument he had in mind was a White-Jude warp field interferometer. An interferometer, in general, is a precision instrument built around a simple principle. Take a laser beam, split it into 2 separate paths, send each path a different way, bounce them off mirrors, and bring them back together. When 2 light waves recombine, they interfere with each other. If both paths are exactly the same length, the waves line up perfectly. If one path is even slightly longer than the other, they arrive out of step. That misalignment shows up in the resulting interference pattern as a shift in the fringes, the bands of light and dark the recombination produces. Interferometers are among the most sensitive measurement tools humans have ever built. They can detect path length differences smaller than the diameter of a single atom. This lineage matters. The Michelson-Morley interferometer, built in the 1880s, used precisely this principle to show that light travels at the same speed in every direction, a result that helped establish special relativity. LIGO, the Laser Interferometer, Gravitational Wave Observatory, uses the same principle at enormous scale to detect gravitational waves. Ripples in space-time so faint they stretch and compress the 4-kilometer arms of the detector by a fraction of the diameter of a proton. White's apparatus was far smaller. The idea was this: surround the laser apparatus with high-voltage capacitor rings arranged in a specific geometry. If warp field theory was correct, and if its effects scaled down to laboratory sizes, the electric fields around those capacitors might produce a tiny local curvature in space-time. Not enough to move the apparatus, not enough to propel anything, but enough in principle to shift the interference fringes by a measurable amount. A twitch in the pattern would be a signal. A signal would be a detection. EagleWorks built the interferometer. They ran the experiment. The results were ambiguous. White's team reported anomalous shifts in the interference pattern under certain conditions. The fringes moved, but the shifts were barely above the noise threshold, and alternative explanations could not be ruled out. Thermal expansion of the optics as the equipment warmed, air currents inside the apparatus, electromagnetic interference from the high-voltage capacitors themselves, vibrations from equipment in nearby rooms. Each one could produce exactly the kind of small fringe shift the team was reporting. Critics noted that extraordinary claims demand extraordinary evidence, and this evidence was not extraordinary. NASA never officially claimed that warp field effects had been detected. The agency described the results as preliminary, requiring further investigation, not a confirmation, not a refutation, ambiguous. But the significance of what had happened did not live in the data. It lived in the institution behind it. NASA had allocated resources to this, built hardware, published. That changed the atmosphere around warp drive research in a way no paper had managed in the decades since Alcubierre's original work. Graduate students could now study warp metrics without it ending their careers before they began. Papers appeared in mainstream physics journals, not in the margins where speculative work usually accumulates. Conferences began, including sessions on advanced propulsion. The field had legitimacy it had never had before, and legitimacy in science is not a small thing. It determines what questions get asked, what funding flows, what a young physicist is willing to spend a decade of their life on. The energy budget had traveled a remarkable distance. Universe scale, planet scale, motorcycle scale, and there it sat. Because 700 kilograms of exotic matter is still 700 kilograms of something no one has ever produced, observed, or confirmed. The trajectory was extraordinary. The endpoint was still a wall, and the question of whether that wall could ever move was still entirely open. But the question was no longer being asked only in papers. It was being asked in a laboratory, with instruments, with data, however ambiguous. That shift, from theory to hardware, carried its own meaning, and it would pull others forward in directions White had not anticipated. Others were already moving, not inside a government agency, not inside a university. Inside an ordinary office building on Madison Avenue in Midtown Manhattan, a small team was doing something different. They were not trying to shrink the energy number. They were trying to reorganize the entire problem from the ground up. The building is 477 Madison Avenue, unremarkable from the street. Inside, a private entity called Applied Physics operates a division known as the Advanced Propulsion Laboratory. Not a NASA program, not a university department, a privately funded research organization backed by investors who understood that breakthrough physics does not follow a predictable schedule. No congressional oversight, no public relations pressure, no budget cycle that demanded results by a fixed deadline. Just a small team with serious credentials and the institutional freedom to ask questions that a government lab might have to justify twice before pursuing. The organization was founded by Gianni Martire, an engineer and entrepreneur with a background in aerospace and technology. His premise was straightforward. Warp drive had been treated for 30 years as a theoretical curiosity, something to be admired and then filed away. Martire treated it as an engineering problem. Map the solution space. Identify which requirements were fixed and which were flexible. Build evaluation tools. Eventually build hardware. The same methodology you would apply to any serious engineering challenge, applied here to the most ambitious propulsion concept in the history of physics. The core team was small, under a dozen researchers, but serious. All held doctoral degrees. All had peer-reviewed publications. Among them, Alexei Bobrik, a theoretical physicist, Jared Fuchs and Christopher Helmerich, both trained at the University of Alabama in Huntsville, Luke Sellers, Brandon Melcher, and affiliated researchers at partner institutions. A compact group, but one that knew the literature in detail and intended to do more than read it. In February 2021, Bobrik and Martire published a paper in Classical and Quantum Gravity, the same journal where Alcubierre had published in 1994. The paper was titled Introducing Physical Warp Drives, and the picture did not hold because the paper did not propose a new design. It proposed something more fundamental, a general framework for classifying every warp drive spacetime that could ever be built, a taxonomy of the entire field. The core insight was this: every warp drive ever proposed, no matter how different in appearance, shares the same basic architecture. 3 regions. First, an asymptotically flat region far from the ship. Ordinary space, the kind of geometry we live in, far from massive objects where physics behaves the way we expect. Second, a passenger region at the center. Also flat, clocks tick normally inside it. No acceleration forces, no time dilation. Physics is calm. Third, between those 2 flat regions, a warping region. A shell of curved space-time that does all the work. It transitions from the exterior universe to the interior pocket. It is where all the geometry bends, all the energy concentrates, all the complexity lives. Think of it like a structured sandwich. 2 calm layers on the outside and inside, and a complex middle layer where the real action happens. The bread is stable, The filling is doing everything. Every design ever proposed fits this picture. Alcubierre's original bubble, Van den Broek's compressed exterior, White's toroidal geometry, they are all the same three-region structure. What differs between them is the warping region alone. How thick it is, how sharply curved, how the curvature is distributed, how it interfaces with the universe outside. Change those properties and you get a different design. But the underlying architecture is always the same. This was not merely elegant, it was useful. Because once you have a classification scheme, you can ask systematic questions. Which regions of design space have been explored? Which haven't? What constraints apply to every design universally? And which are specific to one particular choice of warping region? For 30 years, researchers had been working ad hoc, proposing one design at a time, analysing one design at a time. Bobrick and Martyr gave the field a map instead. And the map revealed something unexpected. There were large unexplored territories. The biggest was the subluminal warp drive, a bubble that moves slower than light. Not faster, slower. For 30 years, nearly all warp drive research had focused on superluminal configurations. Faster than light. That was the dream. That was the whole point. A subluminal bubble seemed beside the point. If you could not exceed light speed, what was the advantage over conventional propulsion? The advantage, Bobrick and Martyr pointed out, was enormous. A warp bubble moving at 90% of light speed crosses the solar system in hours. It reaches Proxima Centauri in under 5 years, and the crew inside it feels none of the journey. No acceleration forces, no crushing G-loads during the push to cruising speed. The flat passenger region handles that. The crew simply exists inside it, weightless and unaware, as the bubble moves through space around them. But there was more. Subluminal designs might satisfy energy conditions that superluminal ones violate. The exotic matter problem, the negative energy density requirement that had plagued every design since Alcubierre, might not apply in the same way to a bubble that never exceeds light speed. A subluminal configuration might not require negative energy at all, not a reduced requirement, not a smaller version of the same impossible demand. Potentially no exotic matter, an achievable design. 30 years of research had chased the superluminal dream and largely ignored what sat beside it. The subluminal direction had been treated as a consolation prize and left almost entirely unexplored. There was a second reveal inside the same paper. Quieter, but just as important. The Bobrick-Martyr framework proved a theorem that had never been formally stated before. Any warp drive, regardless of design, is effectively a shell of matter set in motion. And a shell of matter moving through space is subject to the same physics as any other moving object. It still needs to be accelerated. It still needs propulsion to reach cruising speed. Wait, a warp bubble still needs a rocket. Yes, but what the rocket pushes is different. In conventional propulsion, the engine accelerates the crew and cargo directly. The forces transmit through the structure. The crew feels them. In a warp drive, the engine accelerates the bubble. The bubble carries the crew, but the interior of the bubble is geometrically isolated from the forces acting on the bubble's shell. The crew feels nothing. No acceleration, no inertia, no G-forces during the burn. The external universe sees the bubble move. The crew inside simply exists in a pocket of flat space that happens to be going somewhere. Warp drive is not magic. It does not bypass the need for propulsion. It changes what the propulsion pushes, and it changes what the crew experiences while that happens. The distinction matters, because it means warp drive and conventional rockets are not opposites. They are partners. A warp system still needs an engine. What it provides is a shell that moves without transmitting its motion to the people inside. The Bobrick-Martyr framework became the standard reference almost immediately. Papers published after 2021 cite it heavily. The classification scheme is now used routinely to describe new designs. The three-region language, flat exterior, warping shell, flat passenger region became the shared vocabulary of the field, and the subluminal direction it opened began attracting attention it had never received before. Applied physics had done what no one had done in 30 years of warp research, not built a new design, classified the whole problem, named the map, found the empty territories, The question of whether anything could actually be built there was still entirely open, but it was now a sharper question. And sharper questions are easier to answer. The answer came from within the same team. The same group that had mapped the problem, named the territories, identified the unexplored directions. 1 year after the Bobrick-Martyr classification framework became the field's standard reference, they turned to the territory they had flagged as most promising, the subliminal direction, the one 30 years of research had nearly ignored, and they published what they found. On April 29, 2024, the journal Classical and Quantum Gravity published Volume 41, Number 9, Article 095013. The title was Constant Velocity Physical Warp Drive Solution. The lead author was Jared Fuchs. The co-authors were Christopher Helmerich, Alexei Bobrick, Luke Sellers, and Giovanni Maltese. The full applied physics team focused on a single problem, producing a single result. The claim the paper made was extraordinary. The Fuchs warp drive satisfies all 4 classical energy conditions: weak, null, dominant, strong. These are not arbitrary rules someone invented to make warp drives difficult. They emerge from quantum field theory. They have been tested against observation after observation across decades of physics research. Violating them is not a technicality. It means invoking matter and energy that the universe does not appear to contain. Every warp drive design before this one violated at least some of them. Every single one. The Fuchs design violates none of them. No negative energy anywhere in the structure. No exotic matter. No violation of any physical principle that has ever been observed in the real universe. For the first time since Alcubierre's 8 pages arrived in 1994, 30 years earlier, a warp drive solution existed that did not require anything the universe refuses to provide. Not a reduction, not an approximation, no exotic matter, anywhere. The design works through 2 combined elements. The first is a stable matter shell, a shell with a specific density distribution, built entirely from positive energy material, ordinary baryonic matter, protons, neutrons, electrons, arranged in a precise configuration. Nothing exotic, nothing unobserved. Matter of the kind you are made of, placed in the right geometry. The second element is something called a shift vector distribution. A shift vector is a feature of the spacetime metric describing how different regions of space move relative to each other. Think of it as a flow pattern embedded in the fabric of space itself, not matter moving through space, space itself carrying a directional tendency, the way a river has a current even before anything is placed inside it. In the Fuchs design, the shift vector creates a flow pattern that mimics Alcubierre's original geometry. Space compresses slightly ahead of the bubble, it expands slightly behind it. But the compression and the expansion are not driven by exotic matter. They are driven by the distribution of ordinary matter in the shell interacting with that shift vector structure. Together, these 2 elements produce a warp effect. A region of flat space moves through the surrounding universe. Whatever is inside moves with it. No acceleration forces, no relativistic mass increase, no time dilation for the passengers. The same properties Alcubierre described in 1994, but now achievable with matter that actually exists. The design also uses gravity itself as part of the warping mechanism. Gravity is already curved space-time. A sufficiently dense and precisely shaped distribution of ordinary matter curves space around it. That curvature, combined with the shift vector structure, produces the warp bubble. No exotic physics required. The engine of the effect is geometry, and the geometry is driven by mass we already understand how to work with. Applied Physics evaluated the result using a tool they had built and released publicly, Warp Factory, written in MATLAB, available to any researcher who wanted it. Warp Factory takes any proposed warp metric as an input and computes its properties. What kind of matter would be required? Whether that matter satisfies the energy conditions, how strongly spacetime bends in the design, and it produces a visualization of the geometry. The visualization uses color to show the energy density at every point. Blue means positive energy density, ordinary matter. Red means a violation, exotic matter required. Black lines trace momentum flux through the structure. When the Fuchs metric runs through the warp factory, The output is entirely blue. No red. Nowhere. Not a trace. The momentum flux runs clean through the structure. The curvature scalars behave. Every energy condition holds. Fuchs explained in interviews that prior warp drive models had required matter and energy content that was unphysical. Features nobody had ever observed. Things the universe does not seem to permit. The new approach avoided that entirely. Positive energy, he explained, means phenomena like ordinary matter, light, and antimatter, all of which exist naturally, all of which are detectable and measurable, and in some cases producible. The Fuchs design uses only those, none of the others. The physics community's reaction was cautious optimism. Mainstream physicists reviewed the result and acknowledged it. The solution is mathematically valid. It satisfies the energy conditions as claimed. It represents genuine progress. This is not a small thing in theoretical physics. Papers can be technically correct and still not count as progress. This one counted, but something was wrong, because buried beneath the headline, beneath 30 years of waiting for a warp drive that did not require the impossible, there is a caveat. A caveat the paper states clearly and explicitly, and that Fuchs was careful to repeat in every interview. The solution is subluminal. The bubble moves at constant velocity, and that velocity is below the speed of light. The Fuchs warp drive does not enable faster than light travel. It does not let you reach Proxima Centauri in days. It does not break Einstein's cosmic speed limit, not even slightly. The design that finally, after 30 years, eliminated the exotic matter requirement does not cross the threshold that makes warp drive synonymous with interstellar transport. Not a step below light speed, strictly below light speed, by design. What the paper actually proves is something more precise, and more important for the long arc of the research. It proves that warped spacetimes, as a class of solutions, are not inherently dependent on exotic matter. At least some configurations can be built from ordinary positive energy material, using physics we already understand. The subluminal case is solvable. The field had spent 30 years assuming any physically realizable warp drive was essentially out of reach. The Fuchs result shows that assumption was wrong, not for faster than light travel, but for the class of solutions as a whole. What Fuchs carefully avoided claiming was Star Trek-style rapid interstellar transport. What he claimed instead was the warp effect itself, the ability to move a bubble of space at constant velocity, carrying passengers without subjecting them to acceleration forces, using matter that exists in nature. That is a real and meaningful capability. It is not the capability that fills science fiction, but it is the capability that 30 years of warp research had never quite managed to demonstrate with ordinary matter. The exotic matter problem was not solved everywhere. It was solved for the subluminal case, and left entirely open for superluminal velocities. Whether any future design could extend this result to faster than light speeds, no one knew. The paper does not claim to answer that. The open question is still open. The interstellar FTL dream still has the same barrier it always had, but the landscape had changed. A warp drive made of ordinary matter existed, in theory, for the first time since 1994. And what that meant for the rest of the design space was a question the field had only just begun to think about. That question, what the subluminal result actually means in practice, is worth staying with. 90% of light speed sounds modest when you have spent 30 years dreaming of faster than light travel. It sounds like a consolation prize. It sounds like settling. But turn it over and look at what it actually buys, and the picture changes dramatically. A bubble traveling at 90% of light speed reaches Proxima Centauri in approximately 4.7 years, as measured by clocks on Earth. For the crew inside the bubble, time dilation compresses that further. The subjective experience of the journey runs to roughly 2 years. 2 years there, 2 years back. A mission to the nearest star, completed within a single astronaut's career. Not a generational commitment. Not a relay of crews passing the mission from one lifetime to the next. One person volunteers, makes the journey, and returns while their colleagues at home are still working. That alone would be transformative, but it is not the most striking part. The more immediate effect would be felt inside the solar system, not beyond it, and here the numbers become genuinely startling. A trip to Mars today takes between 6 and 9 months, depending on where the two planets happen to be in their orbits. The spacecraft coasts most of the way. It has to. Sustained thrust would consume fuel at rates no mission could carry, and even if it could, the continuous acceleration would crush the crew. So the ship arcs along a ballistic trajectory, a curved path calculated months in advance, with only limited ability to adjust course once underway. Launch windows open every 26 months. Miss one and you wait. The trajectory is fixed. The schedule is fixed. The crew spends the better part of a year in microgravity, arriving depleted. A warp bubble changes every single one of those constraints. Inside the bubble, space is flat. The crew feels nothing. No acceleration, no forces, no sense of motion at all. It is something like standing on a moving walkway at an airport, the kind that carries you forward without any effort on your part. You're not running. You're not being pushed. The ground beneath you moves, and you move with it, and you feel none of it. Now imagine that walkway accelerating to a significant fraction of the speed of light. Inside the bubble, the sensation is the same. Nothing. Because the crew feels no acceleration, the ship can fire its engines continuously. Accelerate hard toward Mars, coast briefly at peak velocity, decelerate just as hard on approach. The trip takes days instead of months. At high enough acceleration, possibly hours. The crew arrives fresh. No fixed launch window, no locked trajectory. The 26-month wait between opportunities disappears. The same logic extends outward. Jupiter, currently a multi-year voyage, becomes a journey measured in weeks. Saturn, Neptune, the Kuiper Belt, all of them fall within reach of short-duration crewed missions. Objects that today require generational commitments to visit would become accessible the way remote continents became accessible once aircraft replaced sailing ships. The solar system compresses, but the reality was different. There is a safety advantage to the subliminal design that almost no coverage of this topic mentions, and it matters more than the travel times. A bubble moving below the speed of light does not generate a horizon at its leading edge. A horizon, in this context, is a one-way boundary. Think of it as a surface beyond which information cannot travel backward. When a warp bubble moves faster than light, the front edge of the bubble races away from the ship's interior faster than any signal can chase it. The interior loses causal contact with its own leading edge. It can no longer send instructions forward. It can no longer steer the front of the bubble because the front of the bubble is unreachable. This matters for 3 reasons, and all 3 are severe. First, horizons produce Hawking radiation. This is a quantum effect in which the presence of a horizon causes pairs of particles to spontaneously appear, with one particle falling across the boundary and one escaping. For a warp bubble in motion, that escaping radiation would irradiate the crew. Second, the ship cannot steer. Causal contact with the leading edge is gone. The pilot can no longer adjust course, change speed, or initiate deceleration by any means that reaches the front of the bubble in time to matter. Third, particles accumulate ahead of the moving bubble, swept up like debris in front of a moving plow. When the bubble finally stops, those particles release all at once. The result is a concentrated beam of high-energy radiation, not a technical complication. A weapon, pointed forward, fired every time the drive shuts off. These 3 problems are not engineering challenges that better materials or cleverer designs might solve. They are consequences of crossing the light barrier. They are features of the geometry itself when the bubble goes superluminal. And because the Fuchs design is subluminal, strictly and deliberately below light speed, none of them apply. No horizon forms. The crew is not irradiated. The pilot retains causal contact with the entire structure of the bubble, from front to back, at all times. The ship can steer, adjust, and decelerate safely. The drive shuts off without releasing a particle beam. Not a marginal improvement in safety, a categorical one. The subluminal design sidesteps every catastrophic failure mode of its superluminal counterpart in a single stroke. For the first time, there is a genuine engineering path. Not a path we can walk this decade, not a path we can walk this century, but a path which is different from a wall. And yet the engineering challenges that stand between here and that path are not small. They are enormous. Even with exotic matter removed from the problem, the Fuchs design demands capabilities we do not have and may not have for a very long time. The shell of ordinary matter at the heart of the design must maintain a precise density profile under conditions of extraordinary stress, gravitational pressure, thermal fluctuation, and the forces of acceleration and deceleration all work to deform it. Current high-strength materials, the best carbon fiber composites, the most advanced steel alloys, handle pressures up to a few gigapascals. A gigapascal is already extreme, roughly 10,000 times the pressure of Earth's atmosphere at sea level. The warp shell would need to withstand stresses thousands of times higher than that without deforming or failing. We do not have those materials. We may not have them for centuries. Nobody knows what physical structure could hold that shape under that load. The energy requirement is just as daunting. The Fuchs design needs no exotic matter, but it still needs vast energy. Accelerating a massive shell of ordinary matter to 90% of light speed requires sustained power on a scale comparable to significant fractions of total global electricity production. Terawatts maintained not for a moment, but for hours or days. The entire power output of all human civilization, directed at one object, held there for the duration of the trip. Energy on a scale we have never attempted, generated by means we have not built, delivered through infrastructure that does not exist. And before anyone attempts a full-scale warp ship, someone must first demonstrate the warp effect at laboratory scale. That means building an interferometer, a device that splits a beam of light along two paths and recombines them to detect tiny differences in distance traveled, sensitive enough to detect the curvature of space-time produced by a small mass sitting on a table. Current instruments can detect gravitational waves from two black holes colliding billions of light years away. That is a dynamic event, a violent ripple in space-time arriving from across the universe. Measuring the static local curvature around a benchtop mass distribution is a different problem entirely. It requires a level of precision we have not achieved. It requires instruments that do not yet exist. Then, in early 2026, a follow-up paper arrived. The team from Applied Physics and a group of collaborators revisited the warp drive metric families using more sophisticated mathematical analysis. The central finding was this: space-time can bend further than earlier models had assumed. Previous calculations had built in certain convenient assumptions about how a warp bubble's geometry must blend into the surrounding flat universe, assumptions made for mathematical tractability rather than physical necessity. When those assumptions were relaxed, the equations opened up. A wider range of curvature profiles became visible. Some of the newly identified profiles require even less energy than the 2024 Fuchs design. A few might, under certain conditions, permit superluminal operation with significantly reduced exotic matter requirements. Not eliminated, significantly reduced. Enough that the problem might shift from flatly impossible to extraordinarily difficult, which is a different category entirely. The paper did not claim to have solved faster than light travel. It claimed the solution space is larger than anyone had been searching. For 30 years, warp drive research had been methodically narrowing, eliminating candidate designs as they failed energy conditions or stability tests. The 2026 result argued that some of those eliminations were premature. Researchers had been mapping a subset of the actual design space. Regions that had been dismissed as unproductive were worth reopening. Research groups at universities in Germany, Australia, Japan, and the United Kingdom began running simulations in Warp Factory and other numerical tools, evaluating the newly identified metric families against every energy condition, looking for designs that might survive scrutiny. As of this recording, none of them has succeeded. No paper has delivered a superluminal warp drive that passes every test using only ordinary matter. The barrier stands. The faster-than-light problem remains unsolved, but something else has changed, and it is not nothing. Throughout the 1990s and 2000s, warp drive research occupied the outermost fringe of theoretical physics. The mathematics was technically valid and everyone knew it, but the subject carried professional risk. By the mid-2020s, papers on warp metrics appear regularly in Classical and Quantum Gravity and Physical Review D, two of the most respected journals in the field. Conference sessions draw large crowds. Graduate students cite warp metrics in dissertations without stigma. NASA maintains an active interest. Applied physics publishes openly and collaborates with academic groups around the world. The field has moved. Not from impossible to achievable, not in a single decade, but from mathematical curiosity to legitimate engineering problem. The engineering might be centuries away, but it is engineering, not fantasy. And the question of why the superluminal version remains so much harder, why the light barrier specifically is so dangerous to cross, was exactly what the next set of results was beginning to make clear. The question of why the superluminal version is so much harder has a precise answer. It is not a matter of engineering. It is not a matter of energy budgets, material strength, or exotic matter quantities. It goes deeper than any of those. It has to do with what happens at the front edge of the warp bubble the moment it crosses the speed of light. And what happens there is not a complication. It is a fundamental restructuring of the causal geometry of space-time around the ship. To understand it, start with something more familiar. A black hole has an event horizon. Most people think of this as a place where gravity becomes overwhelmingly strong, where some enormous pulling force grabs matter and does not let go. But that is not quite what is happening. At the event horizon, the geometry of space-time itself has changed. Space-time falls inward faster than light can propagate outward. Not pulled, falling. And because light cannot outrun the infall, every future directed path through space-time, every possible direction anything inside can move, points inward. There is no path outward left. It is not that you cannot escape the pull. It is that the geometry no longer contains a direction called out. The horizon is not a force. It is a boundary in the structure of space-time where the available directions have been permanently redirected. A superluminal warp bubble creates something with the same essential character at its leading edge. The front wall of the bubble is moving outward faster than light, which means any signal sent from inside the bubble toward the front can never catch up. The front wall is receding faster than the signal can travel. The signal chases the front wall forever, not metaphorically, literally. The leading edge of the bubble is as unreachable from the interior as the outside of a black hole is from inside its event horizon. The interior of the ship is causally disconnected from its own front boundary. Think about what that means for the crew. The ship is moving. The crew wants to steer. Steering requires sending information to the bubble boundary, adjusting the distribution of energy that shapes the bubble's geometry, nudging the trajectory. But every signal they send toward the front of the bubble falls perpetually behind. The pilot's controls are connected to the rest of the universe in the normal way. They are not connected to the front of their own ship. Any instruction, any correction, any emergency maneuver aimed forward arrives nowhere. It chases the front wall forever and never lands. The ship cannot steer. It cannot adjust course. It cannot transmit any information ahead of its position. The bubble had to be aimed before launch. Whatever vector was set before the drive engaged is the vector the ship is locked to. The crew has no causal access to the space they are heading into. If there is an obstacle ahead, they cannot see it in time to respond. If the trajectory was slightly off at launch, it cannot be corrected mid-flight. The ship plows forward on its original vector, unable to respond to anything in front of it. But something else was happening. Because the steering problem is not the worst of it. A superluminal bubble cannot be stopped from inside. Think about what deceleration requires. To slow down, the bubble's geometry has to change. The distribution of energy in the warping shell has to shift. Changing that distribution requires signals from inside the ship to reach the bubble's leading edge. And those signals cannot reach the leading edge. The same horizon that cuts off steering cuts off deceleration. The crew is locked in at whatever speed the bubble was set to. They are passengers. The pilot's seat is still there. The instruments still function. But the controls leading forward have nowhere to go. The only ways to stop are both deeply unsatisfying. An earlier mission could have pre-positioned infrastructure at the destination, equipment capable of collapsing the bubble from the outside, but that means someone already went there and came back, which requires solving the same problem recursively or traveling some other way. Alternatively, the bubble wall could carry an autonomous mechanism programmed to shut down after a fixed duration. Set the timer, launch, hope the arithmetic was right. Neither option is piloting. Neither option is navigation in any recognizable sense. They are both forms of shooting and hoping. The warp drive in this configuration is not a steerable starship. It is a ballistic projectile. It is aimed and fired. It is not piloted. Theorists have proposed workarounds. One approach is to oscillate the bubble, switching it on and off at high frequency. During the brief intervals when the bubble is off, causal contact with the front edge is restored, long enough to send a corrective signal before the bubble re-engages. The mathematics of this approach exists in some models, but it introduces a different catastrophe. A bubble that collapses and reforms repeatedly may emit intense radiation bursts with each cycle, as the collapsing geometry releases energy the way a compressing spring releases stored force. The energy in some estimates would be enough to destroy the ship from within. Trading the navigation problem for a radiation problem is not obviously progress. The other workaround is simpler and more honest. Accept the limitation. Use superluminal warp drives only as long-range ballistic systems. Aim carefully. Launch. Design the route to avoid obstacles. For a civilization with established infrastructure at fixed destinations, pre-plotted routes between known worlds, this might be workable. For exploration, for missions into unknown territory, for anything that requires responding to conditions discovered en route, it is essentially useless. The horizon problem does not prove a superluminal warp drive is impossible. What it proves is that superluminal warp drive, if it can ever be built, would be a fundamentally different vehicle than the one imagined. Not a starship piloted the way a pilot guides a plane, responding to the environment, adjusting course in real time, making decisions. A ballistic device, aimed before launch, unable to respond, unable to stop. The crew watching the universe blur past through windows that no longer obey the ordinary logic of cause and effect. This is why the subliminal design carries the weight it does. A bubble moving below the speed of light never forms this horizon. The front edge remains reachable. Signals sent forward arrive. The crew retains full causal contact with the entire bubble and with the space ahead. All three of the superluminal catastrophes, the loss of steering, the inability to decelerate, the particle cascade when the drive stops, depend entirely on the bubble crossing the light barrier. Stay below it, and the geometry stays whole. The horizon problem is the first of the deep physical reasons the barrier matters. But it was not the last reason the researchers at Applied Physics, and in the broader theoretical community, were paying close attention to what the superluminal regime actually costs. That horizon does something else. The loss of steering is real. The inability to decelerate is real, but the same boundary that cuts the crew off from the front of the bubble is also doing something the crew would feel almost immediately, something the physics community had understood since 1974, when Stephen Hawking published a result that changed how physicists thought about black holes, about horizons, and about the nature of empty space itself. Before Hawking's work, the assumption was simple. Black holes were perfectly black. No light escaped, no heat radiated. Cold, dark, silent objects that only absorbed. They had no temperature because they emitted nothing. That seemed obvious. It seemed inevitable. Hawking showed it was wrong. The correction came from quantum mechanics. Near a black hole's event horizon, the vacuum is not truly empty. Virtual particle pairs constantly pop into existence from nothing, annihilate almost immediately, and disappear. This happens everywhere in space, all the time, without consequence. But near a horizon, the geometry changes the outcome. One particle of the pair can fall past the horizon, while the other escapes. The escaping particle becomes real. It carries energy away. From outside, the black hole appears to emit a faint thermal glow. This is Hawking radiation. The temperature of that radiation depends on size. Larger horizons radiate cooler. Smaller horizons radiate hotter. A black hole with the mass of our sun would have a Hawking temperature of roughly 60 nanokelvins, 60 billionths of a degree above absolute zero, undetectable against the background warmth of the cosmos, effectively invisible. But a smaller black hole would glow far brighter. A microscopic one would burn with intense heat. The smaller the horizon, the fiercer the radiation. That is the relationship Hawking established. And it is the relationship that turns lethal when you apply it to a warp bubble. That is when the pattern broke. A superluminal warp bubble forms a horizon at its leading edge, not identical to a black hole's horizon, but similar in the ways that matter. It is a boundary where causal structure changes, where future-directed paths cannot cross back. And wherever there is a horizon, the physics that produces Hawking radiation applies. Near the front wall of the bubble, virtual particle pairs split. One particle falls forward into the space the bubble is entering. The other falls backward into the interior. From the crew's perspective, particles rain in from the leading edge, a constant stream of radiation, generated not by any external source, but by the geometry of the horizon itself. Now consider the size of that horizon. Astrophysical black holes are enormous. Their horizons are vast. Their Hawking radiation is correspondingly cold. A warp bubble is tiny next to a stellar mass black hole. Its horizon radius, at something like 10 times the speed of light, would be on the order of feet, or tens of feet. Not light years, not astronomical units. Feet. Temperature scales inversely with size. A smaller horizon means hotter radiation. Theoretical calculations developed in a 2009 paper by physicists at the University of Sydney worked this through in detail. The conclusion was stark. A macroscopic superluminal warp bubble would generate Hawking radiation at its leading edge with a temperature of thousands to millions of kelvins, hotter than the surface of the sun. The crew would not feel warm. They would be bathed in a torrent of high-energy particles pouring inward from the front wall, X-rays, gamma rays, radiation at intensities lethal within seconds. And the faster the bubble moves, the smaller the effective horizon radius becomes relative to the wavelength of the geometry, and the hotter the radiation grows. The natural response is to consider shielding. Put enough material between the crew and the front wall, and perhaps the radiation could be blocked. It cannot. The radiation is generated inside the bubble, in the space between the ship and the front wall. The source is not external. Shielding the crew from the source would require placing material within the bubble geometry itself, which would disrupt the curvature profile that holds the bubble together. Shielding the crew collapses the drive. There is no position inside the bubble that is both shielded from the radiation and structurally compatible with the warp geometry remaining intact. Alcubierre himself has speculated about a possible exit. Quantum gravity, the unknown framework that would unify general relativity with quantum mechanics, might modify how horizons emit. Near the Planck length, roughly 10 to the negative 35th meters, the smallest physically meaningful scale, space-time itself may behave differently than classical equations predict. Those modifications could alter the Hawking emission in ways that spare the crew. But quantum gravity does not yet exist as a finished theory. The modifications are speculative. The radiation problem is not. The subluminal design avoids it entirely. Below the speed of light, no true horizon forms at the bubble's leading edge. No horizon means no Hawking radiation. The crew operates in a calm interior with no particle rain, no lethal flux, no geometry working against them. This is not a minor technical advantage. It is the difference between a habitat and a radiation chamber. But the horizon problem is not the only danger waiting inside the superluminal regime. The second one builds slowly over the entire length of the journey, and it strikes only at the end. Interstellar space is not empty. It is thinly populated. Hydrogen atoms, roughly 1 per cubic centimeter on average, plus occasional helium, occasional grains of cosmic dust, stray electrons and ions, cosmic rays from distant supernovae. At conventional speeds, this medium is negligible. Voyager has traveled through it for 50 years without incident. 1 atom per cubic centimeter is not much. But for a warp bubble, moving at hundreds or thousands of times the speed of light, the geometry changes what happens to those atoms. In 2012, Brendan McMonagle, Geraint Lewis, and Philip O'Byrne worked through the physics in detail. The question they asked was simple. What happens to the interstellar medium when a superluminal warp bubble passes through it? The answer was not simple. Hydrogen atoms and dust grains in the bubble's path do not pass cleanly through the warp geometry. They get caught. The compression of space-time at the leading edge accelerates them to enormous energies. They accumulate, building a reservoir of high-energy matter that travels with the bubble for the entire duration of the voyage. The longer the trip, the more matter accumulates. A journey of several light years would sweep up billions upon billions of particles, each carrying energy proportional to the bubble's velocity. When the bubble reaches its destination and shuts down, all of that accumulated matter releases at once. Not gradually, not in a dispersed cloud, in a tightly focused beam aimed in the direction the ship was traveling, directly toward the destination. The energy in that beam is equivalent to hundreds of thousands of solar masses worth of kinetic energy concentrated into a narrow cone. Anything in that cone would be annihilated. A warp ship arriving at Proxima Centauri would not land gracefully. It would sterilize the star system on arrival. Planetary atmospheres stripped. Surfaces scorched to bedrock. The ship itself would survive, shielded inside the bubble during the release. But the civilization that sent it would have committed an act of interstellar destruction without intending to. This has been called the warp drive genocide problem. The name is sharp, but the mathematics behind it is straightforward. The effect scales with distance traveled and with the particle density encountered. Even the near vacuum of interstellar space, accumulated over light years at superluminal velocity, produces a beam capable of ending everything at the destination. Proposed solutions exist, shaping the bubble geometry to deflect incoming particles around the sides rather than trapping them, dropping out of warp far from the destination in open space, allowing the beam to disperse before the ship coasts in under conventional propulsion. Both approaches add complexity. Both introduce new failure modes. Both require precise planning before departure, arrival protocols, carefully calculated deceleration zones, alignment calibrated to aim the exit beam away from anything alive, and, if a civilization exists at the destination, advance warning that a beam is coming. Stack this against what came before: exotic matter, a horizon that strips away steering and deceleration, hawking radiation that would cook the crew before the journey was a minute old, and now, for any crew that survived all of that, an arrival that destroys the very place they were trying to reach. The original Alcubierre design, the elegant 8-page paper that opened the field in 1994, now looks less like a blueprint for a starship, and more like a description of an uncontrollable weapon that happens to carry cargo. And none of these problems are the last word on what the physics of this regime contains. So the Alcubierre design, as originally written, is not a starship. It is something more dangerous than that. But set that aside for a moment, because there is a question underneath all of it that hasn't been asked yet. What if the problem with warp drive is not the exotic matter, not the horizon, not the radiation? What if the problem is the approach itself? What if instead of warping space around a ship, you cut straight through it? That is a wormhole. And it sounds at first like the escape from every difficulty catalogued so far. The idea is not complicated to state. Ordinary travel crosses the surface of space-time. A wormhole folds that surface so two distant points touch, then punches a hole through both layers. The ship doesn't cross the surface at all. It walks through the hole and emerges on the other side. One mouth in Earth orbit, the other mouth at Alpha Centauri. Step through one, emerge from the other moments later. Nothing inside the tunnel exceeds the speed of light. A photon moving through the throat still moves at 300,000 kilometers per second. The shortcut just makes the effective distance so small that the travel time becomes negligible. From outside, the ship disappears and reappears before any light signal following the normal route could arrive. The universe has been, in a meaningful sense, bypassed. Unlike a warp bubble, the wormhole doesn't move through space. No geometry racing across the galaxy, no compression wave, no bubble boundary. The tunnel is a fixed structure. Two stationary mouths, a short throat connecting them, and the ship flies through. The mathematics permitting this have been around since 1935. Albert Einstein and Nathan Rosen, studying the interior geometry of black holes, found that the equations allowed a bridge, a connection between two otherwise separate regions of space-time. The Einstein-Rosen bridge, as it came to be called, was a feature of the Schwarzschild solution, the geometry describing a non-rotating black hole. Early physicists treated it as a curiosity. The bridge wasn't traversable. It would collapse almost instantly, long before anything could pass through. And even if something entered, tidal forces, The difference in gravitational pull across the length of a body would shred it before it reached the other side. That changed in 1988. Kip Thorne, a theoretical physicist at Caltech, and later a Nobel laureate for the first direct detection of gravitational waves, published a paper with Michael Morris and Ulvi Yurtsever titled Wormholes in Spacetime and Their Use for Interstellar Travel. The work was partly inspired by a request from Carl Sagan, who was writing his novel Contact and wanted a physically plausible way for his characters to travel between stars. He asked Thorne whether general relativity permitted one. Thorne took the question seriously. The answer was yes. Traversable wormholes a spacecraft could actually pass through without being destroyed, are valid solutions to Einstein's equations, provided certain conditions are met. The answer was stranger than expected. Those conditions make every difficulty with warp drive look manageable by comparison. Thorne laid out 4 requirements for a traversable wormhole. First, no event horizon. An event horizon is a one-way boundary. Once inside, you cannot get out. Most natural wormhole solutions, including the original Einstein-Rosen bridge, have horizons. A usable wormhole needs both mouths open, accessible, and connected without any such barrier. Second, a throat wide enough for a ship. In a narrow throat, tidal forces become catastrophic. Picture a body being pulled by gravity at its feet and its head simultaneously, each pulled toward a different wall, with the difference in force growing the narrower the throat gets. Thorne calculated that for human-scale spacecraft to transit safely, the throat would need a minimum radius of several miles. Third, reasonable transit time. A throat where time passes at a dramatically different rate than outside is problematic. Thorne showed this is manageable if the matter holding the wormhole open is arranged correctly. Fourth, and this is the one that ends the conversation as we currently understand physics, the wormhole must be held open. Ordinary matter curves space-time inward. Gravity pulls. A wormhole throat naturally wants to pinch shut under that pull. It is unstable by default. To keep it open, something must push outward, something with repulsive gravity. That means exotic matter, negative energy density, the same substance warp drive needs, and the same substance that may not exist in any usable form. But for a wormhole, the quantities required are much larger. Thorne estimated holding open a wormhole large enough for a mile-scale spacecraft requires exotic matter comparable to the mass of a large planet, arranged in a precise shell around the throat. Any fluctuation in that configuration risks collapse, and if the throat collapses while a ship is inside, the ship is crushed out of existence in a fraction of a second. Compare this to the Fuchs design from 2024. A subluminal warp bubble moving below the speed of light needs no exotic matter at all. The positive energy matter shell holds its shape. The warp effect emerges from ordinary physics. There is no analogous result for wormholes. Every traversable wormhole solution ever written down requires exotic matter in the throat. Every one. The no-go theorems here are stronger than those for warp drive. Subluminal warp has a visible path forward using known physics. Wormholes appear to require a fundamental breakthrough we have not yet made. Some calculations suggest a wormhole large enough for regular interstellar traffic would require exotic matter equivalent to the mass of several stars, concentrated at the throat. If ordinary matter were packed that densely, it would collapse into a black hole. The geometric demands alone are severe enough that most analyzed configurations are unstable. Small disturbances cause the throat to pinch shut in under a second. Anything inside is destroyed. So wormholes, offered as the escape from warp drive's problems, are actually worse. More exotic matter, more fragility, no positive energy escape clause. But here is the thing that keeps both ideas alive. Negative energy is not purely hypothetical. In 1948, Hendrik Casimir, a Dutch physicist at Philips Research Laboratory in Eindhoven, predicted something that had no obvious right to be true. 2 uncharged parallel metal plates placed very close together in a vacuum should attract each other. Not from gravity, not from static electricity. The plates are neutral. The force would come from the quantum vacuum itself. Quantum field theory says empty space is not truly empty. It seethes with virtual particles, popping into existence in pairs, existing for an immeasurably short time, then annihilating. Electromagnetic fields fluctuate constantly. Virtual photons appear and disappear everywhere. Place two metal plates close together, and you impose a boundary on those fluctuations. Certain wavelengths, specifically those longer than the gap between the plates, cannot fit inside. Those modes are suppressed between the plates. They continue to exist outside. Think of the gap as a pipe. A pipe can only carry musical notes whose wavelengths fit inside it. Longer notes are excluded. Those excluded modes still press from the outside, but they are absent from the inside. The result is an imbalance. More virtual photons pressing inward from outside than pushing outward from inside. A net force. The plates are pushed together. This is the Casimir effect. And it is real. In 1997, Steve Lamoureux at Los Alamos National Laboratory measured it directly, using plates separated by roughly 1 micrometer, 1,000th of a millimeter. The attraction was there. It matched the prediction. It has since been confirmed in multiple laboratories with increasing precision. What matters for warp drive and wormhole research is this. The region between Casimir plates has lower energy density than the vacuum outside, lower than ordinary empty space. That means, by definition, it has negative energy density relative to the baseline. It is not a fleeting virtual particle vanishing before measurement. It is actual, persistent, measurable negative energy in a real region of space. The only confirmed example of its kind in all of physics. Negative energy is not forbidden by nature. The Casimir effect proves it. The question is whether it can be scaled up. And that is where the mathematics becomes sobering. A pair of plates, 1 square meter in area, separated by 1 micrometer, produces total negative energy on the order of 10 to the power of -7 joules. 1/10,000,000th of a joule. Less energy than a mosquito uses to flap its wings once. Warp drive designs call for negative energy measured in kilograms of mass equivalent. By E equals mc squared, 1 kilogram of mass corresponds to roughly 9 times 10 to the power of 17 joules. The gap between what a Casimir cavity produces and what a warp drive needs is about 24 orders of magnitude, a factor of 1 trillion. 3 main proposals exist for bridging that gap. None have succeeded, stacking Casimir cavities by the millions. The problem is that cavities interact through coupled vacuum fluctuations. The gains do not add linearly. Different spacings, different materials, different geometries have all been tried theoretically. No configuration has produced a breakthrough. The dynamic Casimir effect, oscillating plates rapidly to convert virtual photons into real ones. In 2011, researchers at Chalmers University in Sweden demonstrated this using a superconducting circuit that mimicked a moving mirror, detecting real photons emerging from vacuum. It was a landmark result, proof that the quantum vacuum can be manipulated to produce real particles. But the power output was unimaginably small. Scaling it to warp drive levels would require oscillating massive structures at frequencies that would tear them apart. Other quantum fields. Nature has more than electromagnetism. The electron field, the quark fields, the Higgs field. Each has its own vacuum structure, its own fluctuations, its own potential for Casimir-like behavior. Researchers have explored whether any of these fields, when confined, might yield stronger negative energy. So far, none has produced dramatically more than the electromagnetic effect. And underlying all 3 proposals is a theoretical constraint discovered in the 1990s by Larry Ford and Thomas Roman, the quantum inequalities. These are mathematical theorems showing that negative energy comes with strict trade-offs built into the structure of quantum field theory. The more intense the negative energy, the shorter it can persist, and the smaller the volume it can occupy. You can have a large amount briefly in a tiny region, or a small amount sustained over a longer time in a larger volume. But you cannot have large amounts sustained indefinitely in a macroscopic region, which is exactly what a warp drive would need. The quantum inequalities do not absolutely forbid warp drives. A loophole might exist. Quantum gravity, the physics of space-time at scales smaller than a proton, might modify the rules in ways we cannot currently calculate. New physics beyond what we know might reveal fields or configurations that circumvent the constraints entirely. These are genuine speculations, not empty ones. On the longest possible timescale, warp drive might not require entirely new physics. It might require extraordinarily patient refinement of the physics we already have. That distinction matters. It is the difference between a door that is locked and a door that is simply very, very far away. And the distance to that door is still being measured. That door is very far away, but it is not locked. And someone has been measuring the distance. Now lift your eyes from the workbench entirely. We have spent this entire journey asking whether humanity might one day build a warp drive. That question is worth asking. But there is a different question folded inside it. One that almost no one had seriously addressed until recently. What if someone else already has? In 2024, Katie Clough and her collaborators at Queen Mary University of London published a paper in Classical and Quantum Gravity. The title was direct, "What No One Has Seen Before: Gravitational Waveforms from Warp Drive Collapse." The paper did not ask whether warp drives could be built. It asked something stranger. If a warp drive exists anywhere in the universe, and if it fails, what does that failure look like from the outside? The setup is straightforward. A warp bubble is a structured region of spacetime held together by a specific distribution of matter and energy. If that distribution becomes unstable, the bubble does not fade gently. It collapses, rapidly, violently. The curved geometry relaxes back to flat in an instant, and all the energy stored in that curvature is released at once. Clough's team modeled this using numerical relativity. That is computational physics solving Einstein's equations on supercomputers, the same technique used to simulate merging black holes and colliding neutron stars, the same events that LIGO detects. They set up a warp bubble metric, gave it a physically reasonable matter distribution, introduced a small instability, and let the simulation run. The bubble collapsed, and as it collapsed, it emitted gravitational waves. The waveform had a specific shape. A brief burst of high-frequency oscillations, followed by a ring down as the geometry settled back to flat. That pattern was distinct from any known astrophysical source, not the chirp of merging black holes, not the signature of colliding neutron stars, not the profile of a supernova core collapse. Something new, something that had never appeared in any gravitational wave catalogue because nothing in the known universe produces it. Nothing in the known universe. Something else was happening. If warp drives exist anywhere in the cosmos, and if they occasionally fail, those failures would send gravitational waves outward at light speed in every direction. Waves that could, in principle, reach Earth. Waves we might be able to detect. There is a catch. Frequency depends on bubble size. For a bubble a few miles across, the dominant frequency would be around 300 kHz, meaning 300,000 cycles per second. LIGO operates between 10 Hz and a few kilohertz, with peak sensitivity near 100 Hz. A warp collapse signal at 300 kHz would fall completely outside LIGO's range. Even a warp drive failure in our own galaxy would pass through LIGO unnoticed, but future detectors could catch it. Proposals exist for high-frequency gravitational wave observatories using different technologies entirely. Superconducting resonators, levitate sensors, microwave cavity arrays, none built at scale for astrophysical detection. But if they achieve their projected sensitivity, they would open a new window on the gravitational wave sky. And warp drive collapses would be a candidate signal, a specific waveform template that search algorithms could scan for. The search for extraterrestrial intelligence has always focused on electromagnetic signals, radio transmissions, laser pulses, infrared waste heat from megastructures. All of it assumes that advanced civilizations use or leak electromagnetic radiation in ways we can intercept. Gravitational waves offer a completely different channel, one that does not require the civilization to be broadcasting intentionally, one that only requires them to be running technology that sometimes breaks. Admittedly, the probability chain has many weak links. Advanced civilizations must exist. They must use warp drives. The drives must fail often enough to produce signals. Our instruments must be sensitive enough. We must be looking in the right direction at the right moment. Multiply those uncertainties together and you get a small number, but not zero. Even a thorough search that finds nothing places real constraints on how common warp-capable civilizations are in our cosmic neighborhood. That is not a failure. That is information. And the work has immediate scientific value entirely apart from the CT angle. By modeling warp bubble collapse in numerical relativity, Clough's team developed new techniques for simulating exotic spacetimes, geometries that violate classical energy conditions. Those techniques are useful for studying black hole interiors, the conditions near the Big Bang singularity, hypothetical cosmic strings. Tools built for one purpose find applications elsewhere. The hunt for faster-than-light travel produces scientific progress as a side effect, even if it never reaches its primary goal. So where does that leave us? 3 decades have passed since Miguel Alcubierre published 8 pages in classical and quantum gravity, and showed that warp drive is a valid solution to Einstein's field equations. 30 years of subsequent research have refined that result, optimized it, and explored its boundaries. The core concept has never been invalidated. Warp spacetimes are real solutions to real equations. And the Fuchs result in 2024 moved the field further. A subliminal warp bubble using only ordinary positive energy, satisfying all classical energy conditions, reviewed and published in a respected journal. Not a curiosity, a genuine result. It means that warped spacetimes, as a class, are not inherently dependent on exotic matter. At least some configurations can be built from the kind of matter the universe actually contains. That is what the mathematics says yes to. What the mathematics still says no to is faster-than-light travel without exotic matter. Every superluminal configuration identified so far violates at least one energy condition. The no-go theorems are not absolute proofs, but they are persistent. Most physicists working in this area doubt that will change. The light barrier may hold for warp drives as firmly as it holds for rockets, for reasons that run deeper than engineering. What the mathematics leaves open is everything between, whether quantum processes can be scaled to produce usable negative energy, whether undiscovered physics offers loopholes, whether approaches not yet imagined will reveal solutions no one has found. Those questions may stay open for decades, or centuries, or indefinitely. The gap between theory and practice is closing in one sense. We understand the problem far better than in 1994. The Alcubierre paper treated warp drive as an interesting curiosity. The Bobrick-Martier framework treats it as a systematic engineering challenge. Warp Factory lets researchers evaluate designs numerically. Numerical relativity lets teams model failure modes. Gravitational wave observatories may soon search for alien warp signatures. These are real tools, real research programs, real papers published and cited in mainstream journals. But the gap is not closing toward a working vehicle. Energy requirements for even subliminal designs remain far beyond anything our civilization can produce. Terawatts sustained over hours or days, focused into matter shells we do not know how to build. The materials science for a stable warp shell does not exist. Substances that handle pressures thousands of times beyond current alloys, maintaining precise geometry under extreme thermal and gravitational loads, are centuries away. And the instrumentation for testing even small-scale warp effects does not exist at the required precision. For a mission planner writing a serious proposal, warp drive is real as a physics concept, because the equations permit it. It is plausible as a long-term engineering goal, because a distant path connects current knowledge to eventual capability. It is not imminent as a technology, not this decade, not this century, probably not for several. The starships of science fiction, hopping between star systems as casually as aircraft cross continents, remain fiction. But here is a distinction that matters. Fantasy and impossibility are not the same thing. A fantasy has no path to reality. It violates fundamental laws. It requires something the universe simply does not permit. A long-term engineering goal is different. It is consistent with known physics. Hard, yes. Expensive, yes. Centuries away, yes. But not forbidden. Warp drive clears that bar. Narrowly. With caveats. But it clears it. Papers appear every year. New designs are proposed and analyzed. Old designs are refined. The solution space expands slowly. one calculation at a time. We may never cross to Proxima Centauri this way. Our civilization might not survive long enough. Some deeper law we have not yet written down might close the door after all. But the other possibility is also real. In some distant century, a research team cracks the final problems, builds the first test bubble, demonstrates it, scales it up, and humanity lights a warp drive for the first time, reaches Proxima Centauri not in 70,000 years, but in years, and then reaches Sirius, and then Vega, and spreads slowly outward into the local stellar neighborhood. Mathematics says that outcome is not forbidden. Engineering says it is not close. The honest verdict is patience. The honest strategy is to keep working. One equation, one experiment, one refinement at a time. A species that walked on the moon, landed rovers on Mars, detected gravitational waves from black hole mergers billions of light years away, and photographed the event horizon of the supermassive black hole at the center of M87 does not abandon a problem just because the numbers look hard. The equations are written, the simulations are running, the instruments are being designed, and the first warp bubble may yet be built, in a future we cannot quite see from here.